All right, hello everyone. Welcome to our first week of the TTP seminar. We have a fabulous speaker today. Before I get there, just really quickly want to remind for all the students, make sure to submit your questions on Canvas. It's basically all you're going to be graded on, so get that in. Okay. So we have a wonderful speaker today, Cynthia Chen. She's a professor coming to us from the University of Washington, where she's a professor in civil and environmental engineering, as well as in industrial and systems engineering, where she's actually serving as the chair right now. Yeah, and she has a wealth of experience in which you're going to hear some of which she'll talk about today, and actually also has some experience with NSF. She was a program director, 5 years ago? Yeah, something like that. So also, if you have questions about that, I'm sure she'll be happy to talk about that. So yeah, I'll go ahead and.
Alan, one more thing.
Yes.
Where
Oh,
did
yes. Sorry. Yeah. Most importantly, an alumni. She is coming back to us from Washington. Yeah. And so please take it away.
Thank you. I was gonna say that my most important label, at least on Davis campus, is that I'm a Davis graduate
Yes.
many years ago. So don't ask me when, it's many years ago. So thank you very much for inviting me back to Davis. And it's always nice, it's a homecoming trip for me. And so my husband will join me later today. And we have a few more days in the area to visit where we lived. And so when I was studying here, we lived in Solano Park. I heard from one of the students is that it's being constructed, right? Under new construction. And when I was here, I studied under the late Reach Kitamura, Pat Mokhtarian, as well as Dan Sperling. They were on my dissertation committee. I did a postdoc with Debbie Niemeyer after before I moved to New York City, and then I moved to Seattle. And travel behavior and human mobility analysis is a field that concerning essentially how people move around in time and space. And when I was studying Davis, and the primary data set we used is household travel surveys, which I think is probably the main data source for many of you who do also study travel behavior as well. And when I was here, the primary method is parametric models such as discrete choice models, as well as other advanced econometrics models. And so these methods continue to be used. About 15 years ago, when I moved from New York City to UW, I had the opportunity to work on some mobile data. And so they are passively generated. They were coming from your mobile devices. And so that's when I essentially broadened my scope of work, both from the data source perspective, as well as from the methodology perspective. And so today, I still work with household travel survey, but my primary focus from a data perspective is those big data. Of course, the quality of data actually has improved from the spatial accuracy point of view. I remember when I started working on these kind of data sets, it was cellular triangulation with a spatial accuracy about 1,000 to 2,000 meters, and that's not uncommon. And today, I think most of the data we work with is GPS data, and they are actually fairly accurate. And also from the modeling perspective, I don't do much parametric models anymore. At least I do not innovate at all on that front. And we do a lot more non-parametric models, and because we're dealing with these kind of data. But one key point that I want to convey with this today's seminar is that through my work, what I found is that behavior insights static data sets such as household travel survey data set still can be very useful in big data moving forward. So anyway, so that's my topic today, is about what I see, the promises and the limitations associated with these data sets. And so this is essentially the outline I have. And I will start with the traditional household travel survey data, which many of you, I think, are quite familiar with. I have the process laid out on the left and some key points on the right. I guess one key point is that it is probabilistic based sampling, which means that on the representativeness metric, it's probably the best in terms of generalizability. And it's also a very rich data set as well, because you design the survey based upon your purpose. And of course, it's complete because it has both sociodemographics data as well as the travel behavior data, but it is very small. So most of the urban regions, I think their sampling rate for household travel surveys is less than 0.1%, and vast majority of the urban regions. And for rural areas, the sampling rate is a little bit larger, but no less than 1%. So that's this one. And I know that many of my colleagues are using those online panels, right? So for example, Qualtrics, Amazon Mechanical Turk, right? And there are a few others as well. And I have used myself as well. Now, the big difference is that it's no longer probabilistic sampling, right? Because people sign on to join those panels and they answer your questions for a fee. And so in other words, it lost that random sampling, randomness nature, which is a core attribute that we need when we want to talk about generalizability. And it has its individual level, it has sociodemographics, and so you can order your sample attributes. You can say, I want 50% of my sample female, 50% male. You can order them and they actually weight them, right? But that does not mean, just because you eventually get a weighted sample that matches your population, it doesn't mean that it is random and it has this generalizability. And one thing that is different from household travel survey, this is that very rarely I see survey data collected through this method has the daily mobility pattern that a lot of us need for demand forecasting. And so the last part of the data that we work with a lot, and this is just a sample, and these are fake data because the vendors do not allow us to show the location, and it is individual, and it's very big, and it's usually the kinds of, for example, this is actually a snapshot from the Boston Metro data, and we are looking at a sampling rate between at least 10 to 20%. And so it's significantly larger than the usual household travel survey. And it does not have, actually, this is wrong, it does not have sociodemographics, nothing on sociodemographics, but it does have indirectly, you can indirectly infer travel behavior. And so these are the different kinds of data. So one thing I want to point out for this data is that this data, so every time there's an event, so essentially what you are looking at, so if this is a household travel survey, every record either represents a trip or represents a activity, right? But this is the big data, so every record represents an event, a network event. And so in other words, whenever you interact, you work on your phone and you go to an app, and an app interacts a network, it generates an event. Okay, and so in other words, that the data itself in such data is not directly activity or travel behavior. It is really how it's a usage behavior, right? It's an app usage behavior, how users interact with apps on their phones or other mobile devices. And that's where these data are generated. And so essentially, based upon this data, we infer where people go and what they do and how much time they spend, right? And so, so in other words, the process of obtaining important travel-related information is very different, right? From this data, it's indirect as, right, as compared to household travel survey where we ask people where you go and what did you do, right? So I made up a table. It's looking at how these three different data collection methods, how they differ from each other. I consider the first two as active, meaning that we actively going out and collect the data of what we want. But the last one, the mobile data, is really passive, right? Because they are not generated because we want to do any transportation related research or any research. They're generated because the vendor needs maintain the billing, for example, right? Because the vendor needs to operate the system, so they need to maintain their records, operational records.
Can we take a picture?
Sure.
Thank you.
I haven't published this, and so I am planning to write a paper and publish this. You're welcome to take a picture. Yeah.
Thank you.
So that's what I label as passive. Sampling method, of course, probabilistic, and none of these other two are probabilistic. Data richness, I consider, they are very rich because we go out and ask information. And this one, I show you kind of the snapshot of the data set. And so they are considered very shallow, right? Because it only has information on lat and long and a time, essentially. And data quality, I said this one, if, NPOs or NHTS does a good job, should be high. And online panel, I think that I've looked at some of the studies using different online panel. I think the quality is quite different. Qualtrics is kind of in the middle. And so this mobile data has, on the spatial accuracy point of view, it is high precision. So that is good, but also it has high sparsity. So I will talk about that as well. On the spatial scale, I said small and very, of course, online panel, you can get a nationwide online panel, but this one is large. And so sampling rate, low, and high, Everson and temporal scale, that all of this, I consider these two as snapshots. So they are static. And with this one, it's not just longitudinal, but it's continuous. I have a second table. And so the consequences of that is that in the end, I think the cost has very different cost implications. And so if you do probabilistic sampling, I think NHTS costs at least $300 per household. I ask my colleagues at PSRC, they do a little bit better job, $150 to $200. But you can even ask for Qualtrics to do, those online companies to do probabilistic sampling for you, but it's gonna cost you a lot. And so the numbers I heard is also at least $300 a person. Big data, of course, if they're generated at the same time, because they're being generated anyway. And so I think depending on how the vendor charges, it can be low. So representativeness, I said high because it has this randomness, it's probabilistic sampling. And this one doesn't, and I think big mobile data also does not have probabilistic sampling, but we are developing methods to fix that part as well. So I said varied. Capturing mobility pattern, yes, no, and yes, right? And data pre-processing is very important that because that this such data is indirectly generated. And so it does require heavy data processing in order to know the trip-related information from them. It's unlike the household travel survey data where you can directly get the number of trips that people make. Suitability, I think for long-term response, these two data sets are good. And the big data set is not very necessarily a good idea for long-term planning purposes, but short-term responses, these two data sets I think are very poor. And it's in this area that the big data has a lot of potential, huge amount of potential. So I said, so promises. I feel that there are a lot of promises, right? Of course, when I say that, because I have a sort of kind of bias because I work on that, but I truly think so. One of the big downside of household travel survey and all of this, one thing that we in the planning field, behavior field don't do is that we always do those static analysis. And in reality, events always happen. So just for example, the last big one is COVID, right? And during COVID period, I remember that our agencies being asked many, many questions by the politicians. And almost the vast majority of them, they cannot answer because they don't have the data, right? And so that is, I said the promises really lies anytime, anywhere, and any population. Like you can do those policy responses and you can evaluate policies and you can simulate responses and you can help formulate responses, and all of that we can't do with the traditional data set, which I see all of those purpose, all of that was a great promise that this big data can have. There are of course many limitations, and so I just list a number of limitations here where they're not necessarily a exhaustive list. So these are just the different things that my lab has been working on because we recognize the limitations. And one is that the data is not very stable. That has oscillations, especially maybe not in Davis, but in Seattle downtown where you have many high-rise buildings, you have oscillation, and it's very sparse. And so even it has become extremely now spatially very good, precise. It's and the last one is that you have to infer. So we have to infer the trip records from the data, and during the process, there are actually many issues, and I will show you that. And of course, it lacks socio-demographic data, and so without the socio-demographic data, it really limits a lot, right, in terms of what we can do. Discrete choice model or econometrics model have been always used to kind of as a way to model household travel survey, and random utility generation. Random utility maximization has always been sort of viewed as an underlying behavior framework, right? To understand, to describe how those trips and activities are generated. But now we're dealing with a complete different data sets, the nature. And so we need, those econometrics models don't work anymore. They cannot be applied. And so we really need to think about what is the underlying mechanism that generates the data. So anyway, so I look at the first thing, the data issues and data stability. So this is data actually in Seattle region, and it's both data sets and GPS and cellular data set. And you can see that just from March 2019 and to November 2019, so it's about 8 months period, we experienced a drop in the GPS data set, right? And so this is the number of individuals. And so this is data stability in terms of the number of devices in the data set. And the second thing is we look at the number of records, so number of events per individual, right? And so you can also see that not only we experienced a drop in the number of devices in the data set, but we also around the same time, we experienced a significant drop in the number of records per individual. And what happened is that per device, what happened is that the vendor has, third-party contracting with those different app developers. And so at any time, those contracts expire and they get renewed, or sometimes they do not get renewed. And so over time, the number of apps that actually agree to provide data, changes over time, right? And also there's also a lot about how the vendor processes the data. And also it's affected by our own user interactions as well, right? Because some of us may actually say, do not share location sharing, you turn off, right? And so all of those uncontrolled factors, and we observe that. And so that's one data stability. And this is actually a Boston data set looking at 2020 and, so about 6 months period. And just right around this COVID thing, we also observe a big reduction in the number of records per user as well. So data stability is definitely something we observe. So this is looking at, so the first one, so this is also Boston data set that already talk about this number of records, and you can see this a clear kind of seasonal effects as well. The number of users, I talk about that, the user days, and so the number of days observed as well, and the number of user days as well. And so here, and also we're looking at this lifespan, the percentage of the high precision data. So, there are different kinds of properties. And then, so this is on this one, and this part is where we're looking at 11 different metropolitan regions across the country. So from very large mega region to large, so this is like New York, Los Angeles, and large, medium, and very small. So these are more sort of rural areas. And we look at how these different kinds of metropolitan statistical areas are with respect to these different data quality metrics, right? And they're different. There's not a clear pattern, but they are different, right? So this is, my next slide is looking at the data sparsity. And so this is actually also Seattle data. We look at from 2018, 2019, and 2019 again. And so this is number of observations per day per device. And as you can see, the vast majority is very little, right? And so on the left, and the same thing here as well. And not only that, if we look at the mean number of records, it goes from 85 in 2018 and drops to 53 in 1 year later, and further drops to 28, right? And so I will illustrate why these matters. The other issue we look at is oscillation. And so this is, again, a real user, and we plot it here. And so you can see all of these are oscillations. So the signals all oscillate around here. And so you have multiple locations. And if you don't address oscillation, you actually will only infer one stay. Because the other stay, all of those algorithms use some kind of a duration and a temporal and a spatial radius to identify states. And so, but actually, we should clean the oscillation, right? And after cleaning it, we identify 3 states, actually. So it matters, right? And so we didn't have this problem if we deal with household travel survey data. And this is even looking at, even the algorithm makes a difference. And so this basically looking at 2 algorithms that I think algorithm 1 is the algorithm we developed in my lab. And this is actually psychic mobility. It's a Python library. And so we are using the 2 algorithms, essentially have very similar philosophy in terms of developing the algorithm. And in this test, we use exactly the same duration threshold as well as a distance threshold. And you can see that, so the black dots are the raw records, right? And those red circles, either they are solid or dotted one, they represent a stay. And so you can see that two different algorithms, two algorithms with essentially the same philosophy and exactly the same distance and the duration threshold, we actually obtain different number of records in terms of the stays. And so, in other words, I previously said that in this inference process, a lot is going on, but unfortunately, unlike household travel survey, a stay is a stay, a trip is a trip, that because all of these uncertainties and most of the researchers in this field using this data do not report this pre-data processing process, but they bring in so much uncertainty. And so we no longer are talking about, a common definition of a trip. Okay, so a little bit of issues about the data. And so part of my lab does is not only, I want to tell people these are the issues that we observe, right? And, but we also want to develop methods to address some of the issues. And so I put them into 4 different categories. And the first one is that we want to understand how these data quality metrics that I showed before have an impact on some of our mobility metrics. And so, so this is where, it doesn't show very well. So actually, somehow the color doesn't show here, but essentially that you can see these different, things, and somehow it doesn't show. So essentially, so this one is, so you can see 3 pies, right? Each one is a 3 pie. And this one is psychomobility. So this left one is psychomobility. And this small mobility analysis workflow is the algorithm developed in my lab. And the last one, H3, is another algorithm that we use. And so we want to look at, so here, so on the left-hand side, we have a number of mobility metrics. And so this part of the variables are sociodemographics. And this part are data quality metrics, right? And so you can see observation number 1 is that, yes, both have an impact, but the data quality metrics seems to have a heavier impact on what is obtained than the sociodemographics, right? That's the first observation. And second observation is that these, depending on what algorithm you use, and the effects are not consistent, right? And so for each algorithm, we use exactly the same distance and the duration threshold. And this is where we actually compare to NHTS data set, and then we calculate the difference in percentage between what we obtained for the region versus the NHTS data set obtained for the region. And so we calculate that, and then we also look at, somehow this doesn't show very well, this thing, but it's very, so it's, the observation is that, again, if we look at this bias between the two, I mean, it's really, I guess, more strictly speaking, it should be the difference between what this data set tells us in these metrics versus the NHTS, right? And how sociodemographics affected and how the data quality metrics affected. I think it's essentially the same observation, is that data quality has a larger effect on the difference between the two. And depending on what algorithms you use, they are very different. And here's another picture where we're looking at this inference, right? And so we're again looking at three algorithms. And so these from the big data, and this is the comparable NHTS data set, right? And looking at how they look consistent with each other on trip rate, dwell time, number of stops, and trip lengths. These are fairly common mobility metrics, and they look very different, actually. And so it's a lot of uncertainty. So here's another one where we're looking at just these how, we want to ask whether different kinds of regions, mega region, large, medium, and small region have any systematic pattern or not in terms of these biases. And clearly they are different and the effects are different, right? On this one. So anyway, so that's the first part we look at. Now, one thing we also did is that all of these algorithms are very so for example, if you use the Python library, the scikit mobility, you can set, for example, the duration and the distance, but it does not allow you to test other things. And so there are other things to test. And so we developed this, it's all open source. And so developed this mobility analysis workflow that allows people who are interested in the data and to test to do sensitivity test to see what kind of impacts that your algorithm will do on your eventual data outputs. And so, for example, so this is an example that we look at. So this is a workflow, right? And so we look at number of trips per person per day, for example. And if you don't do the oscillation, and if you set, for example, time window at different level and how that will affect your number of trips per person, right? And so here we also allow, because all of these algorithms actually comprises different modules. And so, for example, the first module, maybe they first segment the trace into different chunks. And the second module, they may do clustering. And the third module, and you can actually, there's not really a set order that you go from this to this and this, and you can mix actually. And it turns out that mixing them actually can have an impact as well. And so we developed this Docker container essentially to allow people to not only set different parameters, but also to mix, to choose their own workflow. So even you have exactly the same algorithm components, let's say clustering, segmentation, and just having one, different order could make a difference in terms of your outputs. And so we felt like at least that people should know about this. And so that's one thing that we did. The second part of work that my lab did is we did a lot of work in terms of fixing the data. And so fixing sparsity. And so the data is very sparse. We have a very small proportion of the people who uses this phone all the time. And the vast majority, we don't have all the time, of course, and typically the observations are fewer in the morning than in the afternoon and evening, because we use our phones more in the afternoon, right? And also in the evening as well. And so in other words, there's a lot of sparsity. And so this is where we use a multitask Gaussian process, which is a non-parametric model, essentially, to try to fix the sparsity. So essentially to fill in those empty holes in the trajectory. And so I'm gonna pass these two equation slides and so give you a picture. So these are two examples, right? And so, so this is so these solid lines imply the Gaussian process. And you can see that this is a process that is not very good at all because it essentially reverts to the mean, right? But this one fits very well, fits better. So essentially, so the black ones are the observed data and the blue ones are the mean. And so it's very hard to see the test data here. Here's the color, so here's the red here. So essentially essentially what Gaussian process does is that if you have a lot of data, if you have the data, so you see the bound is relatively small, and here's a region that we don't have data, and so the bound is very large. And so one advantage of this method is that it allows us to capture the uncertainty that comes with the data set. And so we did this work, and so we developed the model and try it on a data set of we have. And then we also did benchmarking. Essentially what we did is that we compare our methods. So it's very small. I don't expect you to read. So so this is our method, which is multitask Gaussian process, and we compare against 6 different benchmark methods. And I mean, on all metrics, these are all mobility metrics, and our metric in our method has the smallest amount of error in it. And so that's so I just want to Bill?
I have a quick question. So any of these methods use external data like network data to snap these points to a network or to other?
For this work, no, nothing.
Nothing.
For this work. Later on, I will have a study that we incorporate the physics into it. For this work, nothing, just this data set. So eventually, so essentially we learn first. And then we take a test data set, right? And we take data set, we take data out, and then we predict, we learn. I mean, we use the learned model and predict, and then we compare. So, yeah. But this is only use this data, no other data set is used.
Cynthia, I have a question about sparsity. So how do you distinguish whether by nature that a piece of data should be sparse versus missing data? Because for example, if I look at travel demand between some origin to some destination, there's just nothing going on, so there's no data. But
Nothing going on, meaning like this person is
people are
staying.
not traveling between these 2 regions, let's say, right? So if you look at the demand data, it is sparse by nature. And some of your colleagues actually, Jeff Ben, utilized the sparsity, leverage sparsity
Yes.
for inference, right?
Right.
But sometimes it's missing data, it's a mistake, right? Things are happening, but we're not capturing it. So how do you tell whether it's missing or whether it's just, it should be 0?
Right, but in our case, it's different, right? So in our case, because they are coming from mobile data, so if even if I'm sitting here, my phone should be still generating data. It's just very, random around maybe a location, right? And so in other words, this, when we're thinking about mobility travel pattern, we don't just think about trips. We think about both trips and activities.
So the signal should be always there.
Yeah, the
Okay.
signal should always be there, right? I mean, it's just like household travel survey data, it's 24-hour coverage. Yeah.
But except when there are high rises.
Yeah, but then it's oscillation. So you have data that oscillates, right? So I have a slide here. You still have data, but it just oscillates. So it's like traveling rapidly at 200 miles per hour. Oh, somehow I missed that. So anyway, so yeah, so like here, right? You still have data, they just oscillation. Yeah. Yeah.
And then the metrics right here, this table, these are these out of sample comparisons?
Yes, out
Yeah.
of sample, all out of sample comparison, yes, yes, everything is out of sample comparison, yeah.
Sorry.
Because if it's using the same training sample, it's not meaningful anymore.
How do you read this table? Number of locations is -801.
Yeah, so this is the that's a good question. And the number of, so that's what the number of, I think this is the median error. So it's a comparison, it's a difference between a method and the ground truth. And so -801 is, so we have a paper that demonstrates why why these parametric methods, time series methods primarily does a very bad job when you have like 1 or 2 points only. So that's what it is, yeah. Why it's so big, yeah. Another question? Okay, so the other thing we did is actually we try to bridge gaps between small and a big data. How am I doing in terms of time?
We have plenty of time, so we go up until 3, but obviously you can leave time for questions.
Oh, okay, okay. So I try to finish maybe in 10 to 15 minutes.
Great.
So this is a study that we did quite a few years ago. It was Hurricane Harvey, and we want to predict the evacuation demand. So, and what happens is that the evacuation demand is significantly different or completely different from if today is a day to evacuate. And if you look at traffic data, today's demand is completely different from yesterday's data, right? Because during the evacuation, people no longer go to their usual destinations anymore, right? But by the time, so in other words, if we rely on the historical data, the past data, and to try to predict the demand, the evacuation demand, we're not gonna be successful in terms of that. Probably by the time we detect a huge surge in demand, it's already pretty late, right? So, which to me that even in this case, and just using the big data alone, it's not gonna be that useful, especially if we want to move the window a bit earlier. And so this is where we think that, small data, like survey data can be very useful. So this is an illustration. So we developed this Markov chain model and state transition model essentially. And this is the prediction that for Harvey that we did only using the smart, the mobile data. And you can see that actually, so the red is the actual peak for the evacuation from the data set, from the mobile phone data set. And you can see that it evacuates at the peaks. So I'm sorry, this is probably not Harvey data. This is maybe another data set, I forgot. But so you can see that it peaks around like 25th, right? And if we just use this data set, there's no way, it is Harvey data, I'm sorry, it is Harvey. So it peaks at August 25th on the demand. And prior to August 25th, there's no way we can predict anything because there's no evacuation. There's zero evacuation, like there's nothing to predict. And we could use the data, we started to use the data on 24th. We start to predict and we can see that we actually overshot it, right? We predicted 25th. And so we don't do a good job in just looking at this data. And so what we did is that usually sociologists, many disaster researchers who are sociologists, they actually go out into the field, like rapid survey. I think Miguel did some of that. And they, right after something happened, they go out into the field and they do surveys. They ask questions like, when did you leave, right? Or did you leave? And things like that. And NSF fund those rapid surveys. And after they do the survey, collect the data, they publish the results, right? And so you can, just from journal articles, you can see, for example, hurricane something, so either, how it changes, right? And so those kind of information we found is very useful. And so what we did is essentially we formulate some kind of a Bayesian formulation that we bring in those patterns from the survey data, right? And so this kind of illustrate, right? And so for example, that this is our current time point. And at this time, if we look at, so this data is our big data, right? And we see nothing, okay? We see nothing. So what are the probabilities, right? What are the possibilities? And one is that, well, the next one, because we want to predict t+1 and t+2, and all the way to the end, that we can say, okay, one possibility is that there will be a rapid increase, right? But there's also another possibility is that, the stable demand will continue and then a rapid increase, right? And so we don't exactly know. And here's another situation that we observe, for example, the demand is increasing, but once the demand increases, that we also want to predict not only the surge, but also the drop as well, right? And so the next one could be a rapid drop, or what could happen is that it could continue to increase and then drop. So, right. And so these are the kind of the different situations we formulate. And based on these situations, these are some examples. And based upon those situations, we formulate essentially prior, posterior, those kind of framework. And we estimate that. And it turns out that the result is actually very good, demonstrating that, those static survey data are very useful. And so this is, again, Hurricane Harvey, the same thing. So we have this observed curve is this one, the black curve. And the first part is solid, and the latter part is dotted. And just mean that the latter part, the dotted part is all of our prediction. And so, for example, that we use the predictions made on 24th, meaning that we only use data up to 24th, and then we predict the rest of the curve. And so what happens is that, and we also tested, what if the survey data has errors, right? Random errors. We look at 10% errors, 50%, and even 100% errors. And what we saying, what we find is that, wow, so all of a sudden that we are able to predict the peak. See the peak, our prediction on the peak lines perfectly on 22nd. And that's 2 days before the actual peak. And while previously we're not able to, you can predict a few hours early after you observe, right? And the amount of errors, it doesn't really matter because on all, even though there's a huge error on the behavior curve, but they don't really matter that much. And so, and that's one thing. The other is that the model actually adapts very well because by 24th around the peak, it fits the observed data actually quite well already. And so, so this is to look at this behavior curve, right? So it fits this quite well already. So it adapts quite well. And so that's one thing we look at. We also look at, hey, what if we just take any kinds of survey data, right? And so what we did on this one is that we look at Hurricane Ida's data, right? And we look at Hurricane Irk's data. And essentially the same conclusion is that we are able to predict the peak of the demand about 2 days earlier. 22nd, we're able to make that prediction. And whether this surveying site, so from Hurricane Ida and from Hurricane Irk, doesn't really matter that much. And I think what tells us is that there's value in the static survey data, because the static survey data, they're not useless. They reflect some kind of a systematic pattern in this context. So I have another example, this case and data fusion. So this is a case where we want to use a small partial information to recover the population. So here, what I try to depict are, I mean, it's a little bit hard to see somehow, but the big square represents a population. And these are different colors, I guess, represent different population segments. You can think about older people or younger people, whatever, right? And then I have those diamonds that you cannot see somehow, represent different kinds of environments, right? So urban environment, rural environment. I'll come to you just 1 second. And then I have 3 data sets, small circle, right? And so these are ellipses. Each data set essentially captures a very small portion of the population. So for example, this data set captures a little bit of that, right? And this data set captures a little bit of that, and there may be overlapping of data sets. And so the question is that if I have multiple of those data sets, and because nowadays I think we're dealing with very disparate different data sets, and each data set maybe covers a portion of the population, right? But we as researchers are really interested in knowing the entire population. And so the question is, can we use multiple those biased data set to recover the entire population? You have a question?
Yeah, just to go back to the previous slide, did you notice any changes to the sparsity, oscillations, and stability on the big mobile data side during the hurricane events? And did that affect your, the analysis where the static data set fared better? Because if I think about it, during a disaster event, maybe power lines and phone lines are down, and there are signal disruptions that can increase some of the oscillations as well as hinder stability. Do you do like a comparative analysis of that?
So for this work, before we do this model, we had to infer trips. We had to do the algorithm and infer, oh, this is an evacuation trip, right? So we did all of that. And when we infer trips, we did address oscillation. We did not do the sparsity. We did not fill this trips. Yeah, I mean, we did not fill the data. Yeah. Mhm. So anyway, so that's what have. And so this is kind of the graphic illustration of what I want to do, but this is a word question, right? So essentially that with multiple biased data sets available, capturing a portion of the population respectively, can we develop a methodology to fuse them together and to recover the missing trips? And so I'm bypassing all the methodology again. And what we did is we did a simulation study, and so essentially have 6 scenarios. And the first 2 scenarios are essentially we understand, we capture our model specification, essentially capture the data generation process, right? And then the next 2 we only capture the underlying model generation partially. And the last 2 is basically saying we completely miss it. So in other words, if the model is generated by X1, we completely missed it. We develop a model with X2, right? Now, the only difference between these 2 is that in one case, X2 is not even related to X1. In another case, X2 is related to X1, okay? But you can see that in all scenarios, the amount of missing trips is vast. So we assume that we only observe less than 5% of the trips. And how far can we go and can we recover? And what we found in the simulation data set is that, well, of course, if we can capture the underlying, behavior model, then we actually do a very good job, right? We recover close to 1. So this tells that, hey, all of those behavior work using econometric models and understanding relationships, for example, right? Between social demographics and a building environment and trip generation are very useful, and they can be leveraged in our model to recover them. And in the second case, we missed it, right? So we misspecified the model. So we left something out, and we still do a fairly good job, right? Now, in the last two cases, we completely missed the model, right? And the model says the data is generated by X1, we completely missed it. But in this case, we actually specified an X2 that is somewhat related, okay, to X1. It helps us, I think this is about 50%. So it still helps, right? And so here, so this is actually the case that works very differently in the traditional econometrics, right? Because in traditional econometrics, correlation is no good, right? You want to address correlation. And this is the case that we see that correlation is good, right? Works for us. Now, even this is the case, we completely missed it. And we also completely, X2 has nothing to do with X1, right? It's still, this is about 16%. So we're still recovering 16% of the trips, which is still 3 times, right? I mean, because we start with less than 5%. And we also, so this is on the whole region level, right? And we did it on the zone level, 10 zones, right? And so if we able to recover entire population, the total number of trips in a good way, can we actually allocate those, thing correctly within a zone? And so you can see that we have a 10 zone structure, and and again, the inferred is very small, and these two we overshoot, but in this one, zone 3, we undershoot. But overall, it's not so bad. I mean, we will know that it's a hard problem. It's a hard, it's a hard combinatorial problem. We also look at the real study results. And so we use NHTS. Because with the simulation study, people argue, I could argue, oh, you kind of generate the data yourself, right? And so I said, well, let's do something that the data is not generated by us, right? And so to see how bad, how well can we do. And if we look at the ratio, and we took a small region, downtown, 5 zones, and it's a fairly small region because it's computationally, it's too much going through all of those. And so if you look at this, it's pretty good, right? So this kind of trips recovered, it's around 1. And so the last part I want to talk a little bit about is, I talk about there's a need. In the past, we use econometric models to think about how our trips and activities are generated. But with the mobile data, those methods are not suitable. So we need to develop models that really allows us to understand how these data is generated, right? Because you can imagine that, for example, trips with different modes, walking, biking, driving, or taking a bus, the underlying generation process mechanisms are likely different, right? Just because the physics are different. And so what we did this work is we still look at Gaussian process, but this time we focus on choosing the right kernels. And so, kernels are essentially variance covariance matrix. And so any data, you can calculate their variance and covariance matrix. And so a lot of this is really to estimate this, kernel parameters, right? So to try to find what best kernels really fit. It's like your utility function. It's like when you write an econometric, do an econometric model, you have to write a function. And so then you do some tests, right? So very similar idea. So there are huge kinds of basic, different kinds of basic kernels. I just list a few of them, right? So this is periodic. So my hypothesis is that because of certain attributes of mobility. So for example, every one of us leave home in the morning and return home at night, right? So there is a daily cyclic pattern, right? And we go to work maybe every day or 2 times a week, or maybe we go to park at certain frequency. So there's some kind of a periodicity in our mobility pattern. And so I consider that there's some type, connections between some kind of a kernel with our mobility pattern. And so this work is really looking at what panels, what kernels are more fitting for our mobility panels and what are not, right? The first two kernels are stationary, right? And this one is non-stationary. So, and what's nice thing about kernel is that you can also, this is again, just like trying to find the best structure for your utility function. You can also try to find what is the best structure for the kernels, right? And so these are just two examples, right? And so I have two kernels multiply with each other, but you can also have additions as well, right? And so it's about finding this. And so this work, focus on that. This is a work we also bringing in the network information as well. So speed and bearing, for example. And so to see whether we can constrain our prediction under certain kind of space boundary. And so it's more sort of a constrained optimization. And so this is what we did is that, so this is how we did, so PMT is a physics informed plus temporal. Because if you do not infuse in the physics, the GP model is essentially all temporal, right? Because your inputs are time and the output are let and long, right? So inputs are so only temporal. So we compare this one on all metrics and our model with both physics and the temporal Gaussian process perform better than just temporal alone or just using the network physics data alone. So my last slide is, I think a little bit of reflection is that I certainly want to recognize the data, the big data has a lot of promises, but there are also limitations. And one thing that really frustrates me is that most of the authors doing this work do not report what they did. And I think that individual studies using such data should describe the algorithm, the associated parameters they use, conduct sensitivity analysis, and open source all code. And so all of our paper are open source codes. And research community should also now, I feel like we don't even know what is a trip anymore if they are coming from this data, right? What is a trip and what is a stay? There needs to be some common definitions for that, and probably also develops guidelines in terms of standardizing the process, because especially those information are inferred. So that's one thing that, I think we all together should do. Of course, one big thing, one ongoing thing that we do is that I'm very interested in how to impute mobile data with social demographics. And so that's actually, we just started this project now. And of course, our community has been very good dealing with parametric models. And I think it is also time for us to probably think about the usage of the non-parametric models, especially if we want to understand how this data is generated. And so my last slide is just my funding acknowledgement. Thanks to Yue, who funded my study at NSF. A lot of that came out of that work, and NIH as well funded me years ago, and of course the national centers and tier 1 centers, and very blessed to be part of that, and USDOT as well. Thank you.
Okay, as per tradition, first question from a student. Anyone? You guys have to come up with questions for the for the assignment, so. Okay, maybe we'll open it up. We did get some questions during the talk. Anyone else have?
I,
Yes.
There is another question. I can wait.
No, please.
go ahead.
Thank you for the great presentation. I have one question about the acquisition of data and how much it costs when we talk about the big data. We recently submitted some proposals for the NCSC call, and while we were working on the like funding side of things, we realized household travel surveys became a lot more expensive than we were thinking. The cost per respondent increased if you are doing everything there properly, including the incentives and printing. It's $40 per person.
That's cheap.
Yeah.
Yeah,
Yeah,
I think NHTS is over $300 per household. So if you think about two or three people in a household, that's about at least $100 per person. And I believe if you go for those online companies like Qualtrics, they can do that for you. I mean, if you do probabilistic sampling. If you don't do probabilistic sampling, the cost is between $10 to $15. So that's a lot cheaper if for those online, yeah. So it's a probabilistic sampling that makes it very hard.
and my question is, since doing research became more and more expensive, I'm wondering like your thoughts about the funding side. How cost efficient is it to use big data as compared to household travel surveys?
It depending on your question, I think. So if, if I want to answer, certain questions, you cannot really use certain kind of data, right? So, if I want to ask, if I want to do, we're interested in personalized recommendation system and developing that. And there's no way you can use household travel survey data, right? But there are other cases, I don't think, I think household travel survey data can be reuseful. And especially, but you're not collecting your own household travel survey data, right? We get it for free, so.
For that specific study, what I was talking about is sending postcards to people to get some panel respondents. We're doing an annual panel data collection. And after identifying and getting the addresses, distributing it and providing the incentives to individuals. And I'm glad that it's not $300 because it would be impossible to do the budgeting for something like that for us. So yeah, I'm really interested in the data acquisition part and the funding side of things because it's really where everything starts.
I think it depends on your question. So like Pat Mokhtarian does a lot of attitudinal related work. There's no way you can do that kind of work with big data, right? So it has to be survey. In my lab, I continue to do survey. I do collect my own survey when needed. So it entirely depends on the kind of questions that you want to ask and what do you do with the data set.
Okay, thank you for coming. This is a great presentation.
Thank you.
My question, I was very surprised to see that you could use less than 5% segments to infer the universe. Very impressed. And also because of data constraints, time constraints for some of us, how do you qualify the segments to know they will be useful to cover for your questions? I mean, that's.
I'm not sure if I understand your question.
How similar do the data sets have to be? Or what criteria do you use to be able to overlap or use distinct biased subsets of data?
Oh, so for this one, I guess you're referring to
Yeah, sorry for
this one, right?
Before that one, when the graphic
The
where
picture.
the universe is a rectangle and you have the.
This one.
Oh, this is just abstract. So,
Yeah,
What
maybe
is the
the reference
question?
is the numbers,
uh-huh.
but that is, yeah. Yeah, you expanded on this one and how with that amount of data you were able to infer.
Maybe I can help. My understanding of your question is that Now, let's say you were able to infer the population characteristics. How would you know that, oh, my inference quality is good, right? So what are the metrics that
So
you
we have
use
ground
to-
truths, right? So for the simulation data, I have ground truths, right? Because I generate the data, right? So I have the ground truths, and so I can compare. So I can compare that where the ground truth is, right? And for the real study, I started with NHTS data and I take out data. So from the NHTS data set, I generate, 2 data sets, right? And so I still have the ground truths. So
So what's ground truth?
so the real number, so I know the true number. So-
The number of the population?
Yeah, I know the true number in my simulations, and this is how I evaluate, how good my models is, right? But maybe your question is why I'm able to do that,
Yes.
right? Is that your question? Okay. So the reason I'm able to do that, that's a very good question. The reason I'm able to do that is I mentioned that there are actually useful information in static survey and behavior information. And so in other words, if you think about that, these data sets, and so this might be, for example, a Facebook data set, right? And so the Facebook audience are old now. Not as old as me, but still are old, right? And so that's a target population, right? So if I use this Facebook data set and against their social demographics, I will probably be able to parameterize a relationship between age and a Facebook subscription. I would say, oh, people in the 20s and 30s perhaps are likely to be in Facebook, right? And another data set may be TikTok. And TikTok are very young, perhaps. Okay, I use zero social media, so I don't know. That's my guess, right? TikTok are young, so if I use the TikTok data set and I run regression model and I parameterize the relationship between who belong to TikTok and who belong to, the age, I will find, oh, teens really love TikTok, right? In other words, those behavior insights work for me in my model, okay? So when I only use the Facebook data set or TikTok data set, I understand this parameterization tell me that there's a biased tendency on age of belonging either TikTok or Facebook, right? And so I can, in other words, what I need to recover, if I only use Facebook data set, I know that I'm overrepresenting 30s people, okay? And so my model will work to recover those who are not 30s. And so that's the underlying insight that I used in formulating my model.
So by parameterizing, I don't know, that's where, according parameters to the sample you have, you compensate. So the rest, if you know the average population is 50, you do whatever you need to do to make the rest.
So
be-
in other words, the model
Other
itself is an optimization model, right? So essentially, it's a likelihood function, right? But my likelihood function cannot just involve the observed data. My likelihood function has to include all the observed data as well as the unobserved data. But I do not know the observed data. Right? So how do I write a likelihood function of the unobserved data, of the missing data, right? And so the trick is really to, parameterize this probability of being observed. So what is the probability of capturing a trick, right? So I essentially write a likelihood function that is based upon the likelihood of capturing a trick. And that probability can be parameterized, right? And so that's how it works.
Thank you.
You talked about the fusion of socioeconomic dimension.
I haven't done that yet. I'm starting.
Oh.
So,
So actually, my question was about the.
Maybe
feasibility.
next year, have me back. That's too soon.
So my question was about more the feasibility side of things. Do you think big mobile data right now, have you talked to maybe vendors and vendors who are connected with apps about collecting socioeconomic information along with the?
No, I'm gonna fuse with census data set
Okay,
or
so,
household travel survey. Primarily the census data set.
okay, so
Yeah.
not individual user level.
No, if I
socioeconomic
collect
data.
individual users, then why do I need to fuse it? There's no need
Right.
to fuse. Right. And a fuse with census data, yeah.
I'm wondering, and you just touched on this a little bit, and I think you touched on it a little bit in the pie chart graph with the biases. But
Mhm.
if there are any user groups or like trip types or travel modes that are under or overrepresented in the mobile data. Like I'm just thinking if I'm on the train, everyone's on their phone, right? But if I'm in a car, maybe half the people are on their phone, and if I'm riding my bike, no one is.
Yeah, I don't want to, I know that, yeah, so, okay, so the purpose of my showing this figure is not for people to draw a conclusion about a certain kind of relationship between, let's say, certain demographics, right? And I know we often do that in travel behavior. So for example, we know that female tend to, take more transit, so something like that. That's not the purpose. And I don't think that's what I want to show because it really depends on what kind of data set, right, you have, whether it's from Twitter, it's whether from whatever data set, you could have very different relationship, right? And the message I really want to show with this graph, with this figure, is that really it matters. These data metrics has an impact, and you use different algorithms, they give you different things. And so in other words, because if you're using this data, you cannot just, right now the vendors sell products. They don't sell, there's no access to the raw data anymore. They sell you product, they sell our state agencies products, right? And I feel that very few people is asking any questions about the data. And that's a big problem, I feel. And that motivated my proposal, and thanks to you again for funding it. Yeah, and so actually agencies are not, when I speak to NPOs and DOT, they don't even know what questions to ask. So this project was really motivated by looking at this, not to replacing those vendors, but more sort of, because I recognize there are big promises, right? There's a lot we can do, but really to help the downstream products, really, I think should be helping our agencies with, hey, what questions to ask vendor, right? And what conversation that they should have so that we understand the underlying data sets a little bit better, so that we understand the products that they are selling. That's really what I want to demonstrate.
So I remember a few years ago, you organized a workshop to bring together researchers to push forward this idea of a community-based approach, right? For data fusion, integration, and so on. Through your effort, throughout the effort, what are the key barriers for people to share their data, share their insights, share their algorithm? Most of us do upload data and the algorithm to GitHub. Those who are used to it keep doing it. Those who don't do it will not consider doing it. And so what are the main barriers in our field?
I feel that that's a very good question. I don't know whether my answer is good or not or complete or not. I feel one barrier is really relating to our field, the tradition of our field, and especially with journals, right? Because replication studies are not being valued, which is a big problem, right? And because, so for example, like in travel behavior, there's 3 decades, well, more than 3 decades of history of travel behavior, right? 40, how what we have learned from this 40-year records are influencing real practice. Very little probably, right? And what is the reason? The reason is because, hey, there are 10 studies find positive relationship on one thing. There are another 5 studies found negative. Another 6 find insignificant, right? And why are we having that? Because everyone is doing their own study and everyone coming up with different things and kind of, sometimes they're consistent, sometimes they're not consistent. So we as a community are unable to deliver a consistent message to our stakeholders. So what do we want our stakeholders to do, right? And so what should they do? So we have not been able to do that. And journals do not value studies that replicate others' work at all. If you said, you did a study, I replicated your study and made some modifications, right? Reject,
Right,
that's
make
reject. Immediate, that's reject, right? So this is very different. And that leads actually our citations, usually our number of citation is generally low compared to other fields who value a lot of reputation, right? And because then there's accumulation, there's vertical accumulation. Ours is boom, a lot of studies everywhere. There's very little accumulation. So a lot of that, I think it's ourselves making it. Journals don't value it, right? And faculty need to get promoted, they cannot, right? And so there's no incentive in the system. And there are also, there are no open questions, right? So in certain field, there are open problems, right? Some questions takes the whole community to tackle it. This community is extremely decentralized, and no one is, we don't have consistent community effort to work on certain open problems that are very important, that could change the state of practice. That's my view. I don't know how to change that.
But yeah, I do share that concern. The lack of a comparison study.
Yeah, there's no comparison,
Yeah,
but very little comparison.
Yeah, if you look at the AI, right, machine learning, it has this standard library that people can say, oh, I claim my algorithm being better. I will check it, test it against this standardized library. We don't have that.
Yeah, very, very few. I mean, I think the network modeling community does a little bit better than the behavior community in terms of at least you guys do benchmarking.
Right.
We don't even do benchmarking. And in traditional studies, behavior studies don't even bother with benchmarking, right? So it's very unfortunate.
Yeah, potential research ideas
Yeah.
for future students.
I think there were comments or questions. Yes.
I was gonna say, so it is 3 o'clock, so we want to be respectful of folks' times. I think, Cynthia, will you be around for a little bit?
Yes,
Yeah,
yes.
so anyone who's interested in engaging and continuing conversation, please feel free to hang around. Otherwise, let's please thank Cynthia.